we're still in chapter 5, and what I want to look at next is uniform circular motion. And so, just put simply, it's this kind of motion here, where you're going around in a circle, but you're not accelerating the speed. The speed of the motion as it goes round and round stays constant. Okay, and so the radius is constant and the speed is constant in uniform circular motion. And so if we draw a radius vector looking like this, this would be the center of spin. Here's our mass going round and round. So at any given point then, there's a velocity vector that is tangent to the circle. So the velocity is not constant, but the speed is. And so that isn't a paradox. All that means is that the length of the vector is staying constant. But because it's uniform circular motion, the direction of the vector is constantly changing. And so that creates an acceleration too. Remember that our definition of acceleration is a change in velocity. So there's two ways you can change velocity. You can change the speed, which we're not doing here. Or you can change the direction, and that is what we're doing here. Remember, Newton's first law tells us that an object will travel in a straight line at constant speed unless acted on by an external force. So that straight line constant speed means constant velocity. And so one way to accelerate then is to change the direction. And when you do that, you don't necessarily have to change the speed. Now the speed can change too, but that's a little more complicated. We'll get to that in a later chapter. And so for the moment then, we'll just imagine that this thing, as it goes around, has the same speed, but the direction of the velocity vector from moment to moment is changing. And so our goal then in uniform circular motion, first of all, would be to, let's find the centripetal force. Let's find the force necessary to create that kind of an acceleration. Well, to find the centripetal force, that's going to equal mass times centripetal acceleration. So we need an expression for centripetal acceleration. So the way that I'd like to do that is to, first, let's imagine that we're just looking at this mass at 2 points that are somewhat nearby to each other in space and time. Okay, so at this later time, we've got a theta here that has been swept out. And the velocity then has changed its direction to that direction. But what we can do here if we want is we can say that v here plus delta v, and delta v has to go inward toward the center of spin, has to equal v final. Okay, so this is v final here. This is v initial, but the length of these velocity vectors is the same. And then this extends to the center of the circle. Okay, so if this angle is theta, and this is a tangent to the surface that rotates to be in this tangent, then it must have rotated through that same angle theta. So basically then what we've got here is an isosceles triangle that looks like V, V, and delta V. This is delta V, this is V final, this is V initial. Okay? And this angle here is theta. Now, the Greeks a long time ago, worked out that the ratios of the sides of similar triangles are equal. And so what we've got here is a distance triangle that's R, R, and then this little arc length here we can call V delta t, because it's traveling with a certain speed through a certain amount of time that it takes to travel through that distance. So if I want to compare those two then, this is R, R, and then V delta t. That's the distance. That's like our little arc length distance that we've traversed. Just rate times time equals distance. And then this angle is theta. So this is also an isosceles triangle. Well, you say, wait a minute, not quite. This chord would make a similar triangle to this one, an isosceles triangle, but it's a little curved on the top. That's true, but Isaac Newton was able to show that in the limit, as delta t goes to 0, this becomes, this distance and that distance are the same. They're the same distance in the limit as delta t goes to 0. And Archimedes also showed that with his method of exhaustion for computing pi. Okay? And so as long as we take small times, we can say that this triangle is similar to that one, and we know that the ratios of the sides of similar triangles are the same. So we can say that delta v is to v as here v delta t is to r. This side is to that side as that side is to that side. And so this gives us an expression then for our centripetal force if we, or centripetal acceleration, if we just write delta v delta t is equal to v squared over r. But this isn't quite true until we take the limit as delta t goes to 0. It only approaches that because the arc length distance and the chord aren't the same length unless we go to the limit as delta t approaches 0. And so what that gives us then, by the definition of a derivative, is dv dt. And this is a special kind of acceleration that we call our centripetal acceleration, AC. So that's equal to v squared over r. Now, our centripetal force then is going to be m times AC, or mv squared over r. So that's our expression then for the centripetal force. And so how does that work? Well, that force always acts toward the center. That's why we call it a centripetal force, like a center-seeking force. So as the mass moves around in this circle, the tension in the string is always a vector that points straight away from the mass in the direction of the string, which is pointed toward the center of the circle. And so the centripetal force is always acting toward the center of spin. And so it takes a certain amount of force then to keep something moving in a circle. And so here I've got a little scale. So I'm going to move this thing around. And as I go faster and faster, I hope maybe you can see that the scale is moving. Okay? And so what that's showing us then is that I have to exert force to make that mass go round and round in a circle. If somebody were to cut the string, or the string, even worse, were to break, oh my gosh, if the string were to break, then we're in trouble, because as this thing goes faster and faster, it creates more and more tension in that string. Say if it broke at this point, then it would take off at a tangent to the circle in a straight line. Okay? And so at that point, we would no longer have uniform circular motion. Okay, so with that in mind, let's do a simple problem where we've got a mass, and that mass is going round and round in a circle. And let's give some values for the radius and for the mass. Okay, so here let's say m is 2 kilograms. Let's say that the radius r is equal to 1/2 meter. And let's say the velocity v is equal to 1 meter per second. Let's find the force, Fc, necessary to keep it going in a circle. So this is the centripetal force necessary to maintain this motion. And we know a relatively simple equation. Our centripetal force is mv squared over r. So just plug and chug. We've got all the numbers that we need here, and so we'll just plug them in. This would be 2 kilograms times 1 meter per second squared over 1/2 meter. 2 times 1 squared over 1/2 would be 4 newtons. So I would need to apply 4 newtons worth of force, which isn't quite a pound's worth of force. I think it's 4.5 or something newtons is equal to a pound. But here we'd have to apply that amount of force, but we'd always have to have it pulling in toward the center. So Fc here, Fc there, as it goes round and round, have to be 4 all the way around for this to work at that speed. But now, let's double the speed. Let's find the new Fc. Okay, so if I start going at twice the original speed, then I'm going to really have to hold on tighter, because this thing is going to want. So now I've doubled the speed, but I can tell how much harder I have to hold on to this thing, and that scale is going to have moved proportionately more. It's not just going to double. Okay, so we double the speed. The new Fc is going to be m, 2 kilograms, times v, which is 2 meters per second, because I've doubled the speed from 1 to 2. I square that, so it goes like the velocity squared. So, but the other values are the same. 1/2 meter and the 2 kilograms are the same. So that shows us that it's 4 times the original, or 16 newtons. Okay, so doubling the speed means that Fc final is equal to 4 times Fc initial. And if I tripled the speed, it would go up by a factor of 9. So it gets harder and harder to get the object with the same mass and radius to go round and round in a circle as the velocity gets higher. So let's look at another example. There are plenty of these that we can look at, but one of my favorites is the rotating space station example. In a rotating space station, we can simulate gravity. And so this is really kind of good to do, if you can, because when astronauts go out into space, they're in a weightless environment. They've got many difficulties that they have to overcome in the zero-G environment. Of course, there are radiation problems, but there's also the problem of just not having that gravity force to fight against like we're used to doing on the Earth. And so your muscles start to deteriorate, even your heart muscle. Your bone density drops too, because underweight, that's how you keep your bones strong, you know, doing a lot of walking and exercise is good for your bones. And so if you're not making up for that in a zero-G environment, then your bones can start to fall apart. And so you've got those kinds of things happening, as well as you're getting zapped by radiation at a pretty intense rate. And so all of those things act in a similar manner to accelerated aging. And so this is a way that we could fix that problem. Now, you might wonder, well, why didn't we do this with our International Space Station? And the answer is, I wish I knew, but I think it had something to do with going into partnership with the Russians. And so we had to bail them out a whole bunch of times financially. And so we ended up spending something like $70–80 billion for just a bunch of bolt-on modules. Basically a big pile of junk. If we, I'm not saying it's worthless, but in comparison to what we could have had, a really cool rotating space station like what you saw in 2001, if you ever saw that movie with Arthur C. Clarke, wrote the book for that. But anyway, here we go. So we're on the outside edge of this as the space station rotates around like that. Okay, so let's say that that's happening. So as that happens, then we're going to tend to move this way, but then because we want to go in a straight line at constant speed, the space station's floor starts pushing up on us because of the fact that we want to go in a straight line and the floor is kind of getting in our way. And so what that's going to do is that's going to cause the floor to push up on us with a normal force. And so that normal force at each point along the path is going to point toward the center of this rotating space station. And so that's your normal force. So you have F normal. And even though you might be weightless up there, you can simulate gravity with a normal force that is basically caused by the fact that you want to go in a straight line and the floor is getting in your way. It's accelerating you and pushing up on you. And so that simulates the effect that gravity has on you on the surface of the Earth. So if we want to find the tangential speed, vt, here, so that's the velocity that you'd be moving at the outer edge of the space station. Then, all we really need to do here is say that our centripetal force is equal to the normal force, because that's the only force that's acting here that makes you keep going in a circle. So for you then, this isn't down, it's away. In general, that's not down, because even when you're up here, your hair isn't going to fall toward the center, because down for you is away from the space station, from the center of the space station, okay, like that. So here would be the F normal here. So that F normal has to be by our centripetal force equation equal to mv squared over r, but of course it's pushing you up to deviate your straight line path into this curved path. And so what we want, if we want to simulate gravity, is we want the centripetal force to be equal to your weight. Okay. That's our condition then, is that the centripetal force has to equal mg, and then we can solve for the velocity that makes that possible. Okay, so we'll set this equal to mg, and fortunately this mass cancels, which means that you can simulate anybody's weight because they'll have the same acceleration as if they were under the influence of gravity on the Earth. And so therefore, v would equal the square root of rg. Okay, and so let's say that for this space station, our R value here is 1,000 meters. Then v would be the square root of 1,000 meters times 10 meters per second squared. So that'd be the square root of 10,000. Okay, and so I could go check out what that is on my calculator, but then, well, wait a minute, 100 squared is 10,000, so I don't even need my calculator for this one. That's 100 meters per second, or about 200 miles per hour at the outside edge. But the radius is 1,000 meters, so that means 2 pi r, that'd be about 6,000 meters, and you'd be all the way back around to your starting point again. So this would be a pretty big space station. Okay, but it would be cool, because you would have simulated gravity. You could run around this thing, you could do laps, and it'd be like doing laps on the Earth. If you threw a rock, that rock, it would seem like it's going in a straight line, but because the floor is curving up toward it, what it would look like from your accelerated point of view would be a parabolic path going down to the ground. And so a lot of the aspects of the acceleration here would be difficult to distinguish from actually being on the Earth. Although there are some things that would be different. Let's say if this thing's going at 100 meters per second relative to someone that's not rotating with the space station, then you could turn around here and throw something this way at 100 meters per second relative to you. Okay. But relative to somebody that's out here looking, it wouldn't be moving at all. So it would just stop, and you would go all the way around like this, and you would come around. If you threw it this way, you'd come around and it hits you in the back. So that would be a little different from being on the Earth. Although, you know, it's because the radius of this thing is much smaller than the radius of the Earth. But there would still be a lot of things that would be similar. And then another thing you could do is, in a space station, it's really nice if you still do have a zero-G area, because you can do a lot of really neat experiments in zero-G. You can make different kinds of alloys combine and stuff that would not usually combine under the acceleration due to gravity. And so you can get new kinds of materials, and you can look at different laws of physics and stuff. They've actually, by looking at little specks of dust that were in this envelope that they brought up with them, they saw that the specks of dust were starting to clump in a zero-G environment. And they just had a bunch of little goofy experiments like that, and they didn't know which ones would be interesting. He goes, well, look at this, you know, a bunch of dust bunnies have been built up in here in this zero-G environment. And he goes, you know what, you've just solved an important problem in planetary formation, because it turns out those electrostatic forces are overwhelmed by the force of gravity, but if a planet is first trying to form, it can form out of these little clumps of gas materials, hydrogen gas and stuff, that start to coalesce together like the little dust bunnies do. And so that's how planets get started in their formation, is by being able to clump together in a zero-G environment. So anyway, it's nice to have that zero-G environment. It turns out you would have that if you went to the center of the space station. But as you start to climb the ladder toward the center of the space station, we might ask, well, what happens when you get to the midpoint? What would be your apparent weight here? Okay, well, the centripetal force equation goes like mv squared over r. So if you're going to that midpoint and you're climbing up that ladder, at first you're going to have your regular weight, because it's going to seem like your regular weight. But by the time you get to here, you're going to be at a distance away that's equal to r over 2, and your velocity is going to be v over 2. And because you're going this half the distance, 2 pi r, right? But r now is half as big as it was. So the velocity times the time, that's how long it takes to go around once, equals 2 pi r. So if r goes down by a factor of 2 and the period stays the same, it means that v goes down by a factor of 2. So that means we're at v over 2 when we're at r over 2. Half the speed, half the distance traveled in the same amount of time. So if we plug that into our centripetal force equation, that's going to be m times v over 2 squared divided by r over 2. That's going to be 1/2 mv in original squared over r, or 1/2 mg. Because this mv squared over r that we had originally was the original centripetal force, which is mg. But now, because the velocity's been cut in half, and you square that, I mean, this is v squared over 4, but this is just r over 2. So you get 2 over 4, or 1/2. And so you're only at 1/2 your weight at the midpoint. And you don't have to accelerate at all at the center. And so that's why the apparent weight is 0 at the center. It's 1/2 at the halfway point, and it's your full weight at the outside point. So if you fall down one of these things, you fall out of one of these things, you're kind of floating in here, then you slowly start picking up weight, and then you have your full weight by the time you hit the floor out there. Okay, so that's the space station example.